Hello, everyone. This is lecture 11 of PTRE 465531, Petroleum Reservoir Geomechanics. Today, we will start module 2, as I promised last time. I did upload the homework 2 last night, and homework 1 is due tonight, 11:59, 1 minute before midnight. I uploaded homework 2 earlier than what I expected. I want to give you more time to review everything before my office hours tomorrow, because even though you don't know how to solve all the questions so far, I have it tentatively due, not tentatively, I have it due on October 1st, which is next Tuesday at 11:59 at night. So you have 2 office hours to take advantage of until this homework is due. The thing is that the first exam is on the October 4th, which is next Friday, basically, not this Friday, the Friday after. That means you have a homework due on October 1st, and then an exam on that Friday. There is not a lot of students in the class. And I will see with the administration ladies if it's possible, and if it's possible to move it like something like October 9th, because this semester started 1 week later than last year, and I want to see. I don't promise anything. However, if there is a reason you guys don't want to move it, and either you book an appointment and you want to keep it on October 4th, that's fine by me. It's just I want to give more time. And actually, because I know where people got stuck last year, I tried to give like more time into those topics that people were getting stuck, so that we are not really I have experience now teaching this class, so it's like I don't want to rush through important matters. Anyway, so let's start with module 2. Like we said before, module 2 is gonna be all about constitutive relations in regards to, we are gonna be relating strain and stress and deformation on the REV. REV, what was it? Representative element volume. And so on. Yeah, so it's all about, and it might be a good idea to refresh your memory from solid mechanics, because all the equations that you have seen in solid mechanics relating stress to strain, strain is a dimensionless quantification of deformation. They are all gonna come back here, and it's gonna be just applied to rocks. Anyway, so solid continuum mechanics is basically the branch of mechanics, of solid mechanics, that we would be using in this module. It's a branch of solid mechanics dealing with transmission of forces and deformations of solid materials, modeling them as a continuous mass rather than discrete particles. Foundation of stress-strain relations, i.e. constitutive relationships, telling us how solids deform under stress and vice versa in rocks. Boundary conditions, these are the stuff that we talked about in the previous module, and also some more of stuff that we are going to talk in this module, like stresses on the boundary, like the in situ stresses, S1, S2, S3, SV, SH max, H min, etc., etc. Boundary forces, like gravity, is also body forces, forces that are exerted by an external sort of an external, they have an external source. And we are going to talk about this guy Cauchy is a very important guy in this topic. It's so important that his name is in the Eiffel Tower.
Cauchy, yes.
Yeah. You've been there?
Yeah.
You saw it? It's on the edge, right?
Yeah, exactly.
On the very left.
And he did some stuff in Algeria too, so.
Oh, really?
Yeah.
I didn't know. I know he was a civil engineer, but he was very mathematically inclined, and Lagrange was his neighbor. And he told his dad, don't show him a mathematical problem until he becomes 17, because he didn't want anybody else to like teach him wrongly. And he did. He was very active in the publication world. Like, he was publishing a lot. He published like 800 papers, because his wife's family were involved in a journal. Like, they were publishing his work basically because of his wife's family, like his in-laws. What happened also? Like, he has a lot of principles in linear elasticity named after him. And even before his death, he said his last speech at the schools he was a professor. He said that I will publish this I will prove this in my next publication. So he was working on something at the time he died, which never got published. But he started as a civil engineer, and then he got into mathematics and physics. He went from applied to more theoretical, which is a lot of people who do that, who go from application to theory. I know the more normal is to go the other way. A lot of people who go like this, they end up being very good for some reason. Anyway.
Experience.
Yeah, that's true. And also they understand the application, so it's like their feet are on the ground in a sense. But he started from somewhere, right? To come up with what is called equations for stress equilibria, or equations of motion. He had to start from somewhere, and basically that somewhere is the Navier-Stokes equation of momentum balance. And he manipulated it in a certain way. And I don't think you take a class here on transport phenomena, but I remember when I was sophomore and I had to take a class on transport phenomena, which was very hard, until we all realize that there is a certain pattern in the problems. And basically, you go in the back of the book, you find the appropriate equations, and it's like big, ugly equations. And you take them and you start applying them to your problem, and you basically cross out terms, you make them zero, and then it becomes something very simple. And but this is where he started from. We will see sum of forces in every direction, adding it equal to zero, a force balance. In Cartesian coordinates, you have fx, fy, fz. They should all add up to zero. So the summation of each one in each direction, principal direction, would be zero. And this is where he started. So this looks, we're going to see in detail the summation of forces in the x direction. And then the analogous thing happens in every direction, basically, okay? So here you have the REV. It has dimensions dx, dy, dz. And then we are looking only in the x direction. So the only normal force, normal stress exerted on it is sigma sxx, okay? In this direction. So it's, how do you call it? It's exerted on the surface area dy by dz, right? It's exerted onto this surface area. Dy by dz, not dx, right? So we have this term, okay? And then we need to make the balance of the other side. So we have Sxx on the other side, but we may have change in the a change in the stress as it goes through the REV, okay? And this change, I mean, it may not be the case, but you need to have your equations such that they can take into account of it if it does take place. So you have the derivative of Sxx with respect to dx. So does my Sxx change as I'm moving through the REV in the dx direction? If yes, this term would be non-zero. If no, this term would be zero and goes out of the out of the way. Then you will only have this and this, so they will cancel out, and you have basically equilibrium in the normal stresses in that direction. Okay, let me erase, make more space. People online, stop me if you have any questions, also in class. Then we have the shear stresses, which are a little bit more complex. Okay, SYX is the force acting on a surface perpendicular to the y-axis. Perpendicular to the y-axis. That means in the dx dz dimension. And then you have the force on the perpendicular to the y. The first term y is like telling you it's acting in the y perpendicular to the y direction. So if it's perpendicular to the y direction, it means that it's the other two. So dx dz basically. And then the second subscript x is basically the direction into which this shear force is acting. Okay, and you can understand that the purple arrow is parallel to the orange. So it's they are both forces acting in the x direction. After all, we are doing the summation of the forces in the x direction, but this one is exerted on the plane that is between is perpendicular to y, so x and z. So it's, let me use the opposite color of orange is blue. It's acting here. This is what the first letter is trying to tell you.
It's tangential to the plane.
Yeah, exactly. It's the shear. Like this. Okay? And of course, this can change as we move along this plane. So you have the second square brackets. It's similar to the above. You will see how does it change with respect to y. If it changes, it might not change, then it's zero, okay? And you multiply that by where it's acting, dx dz. And now, the other one is this. What do we have? SZX. So the first letter is the plane it's acting. So if it's acting on the plane of Z, I need to look at the other two. So dy dx. I'm looking here, basically. It's acting in this surface. And it's in the direction of x. Again, it's perpendicular to the other two arrows, right? This arrow is perpendicular to this. It's perpendicular to this. But this one is acting normal to a surface. This one is acting tangential to a surface. As Hakim said, it's the orange is shear, purple is normal. Same way, it might change as you move along dz, because you are comparing this with the one at the bottom, basically, which you can see.
SCX.
Yeah, is it wrong? I think the first is the where it's acting, and then the direction, if I'm not mistaken. I might have a typo, but I think that most of the important mistakes are
I know that
already.
there is one perpendicular and two tangential.
For all the surface.
Yes.
Yeah.
If SXX should be perpendicular, those are,
The
so,
low-
so we have one perpendicular, two tangential, right?
Yeah, that's true. That's true. That's
So SXX should be perpendicular to the X plane, right?
S X X. Yeah,
Yeah, which is.
which is
dy
this is the X plane. So this.
Yes,
Yeah.
and then we have SYZ, SYX, SYZ. No, SYX, SZX, they should be on the same plane. Yeah. Because if SYX is perpendicular to dy, then SZX should be perpendicular to ZZ, right?
No, you want your SXY, SYX to be SXY basically. And you want ZX to be SXZ.
I think SZX should be this. Because SYX is perpendicular to dy, then SZX should be perpendicular to
No, they are all acting in the X direction, but the other letter
In the
below
plan Y, X and.
is perpendicular to is the direction perpendicular to the plane, because I cannot say plane of ZX here, but I'm telling you Y, and you are saying, okay, what is perpendicular to Y is ZX. So basically this is saying, look at the other two for the plane. So basically, oh, XZ plane. So XZ plane,
Yeah.
this one.
The plane, yes.
And then this one says XY plane, and it's supposed to be this. Do I have a mistake?
No, it's true, it's Y plane,
XY and XZ.
yes. The plane is that.
Yeah.
But
I will
it's-
check my notes.
But it's parallel to YX plane,
Yeah.
yeah. The stress, the shear.
Yeah.
It's in the same direction as YX.
It's in the same direction. Or you want it to be facing the other way, basically.
That's what I guess he
Or
wants.
he wants the arrow to be pointing.
Yeah,
that way.
I don't know, yeah.
Yeah, it could be. I mean, but that would be basically, it's got to be a negative value on the magnitude, basically, of the.
Yeah.
Yeah, you can reverse it. Yeah, very easily. I will check my notes and see if I drew it correctly from
I
that.
guess I understand what you mean, yeah, but you're talking about the direction of.
Yeah, he was
the
talking
shear
about the
stress.
direction. I thought he was talking about the subscripts. Okay, and we now have an extra term here. This is the accumulation term. Okay, forces created within.
Forces is all.
No, that's the density.
Ah.
Forces, the whole thing is that I circled, that's a force.
Yeah.
Okay, it's a force in the X direction.
Mhm.
Okay, and it's acting throughout the volume. The whole thing, can I say this REV may have a force acting in the body somewhere, in the X direction in this case. I need to take account of it. It might be zero, but it's basically a force caused by an acceleration, right? This A causing the force. Rho is the intrinsic property of the material, the density, and it's acting on the whole volume, so dx, dy, dz. Yeah, it's the Newton's second law, basically. So we did the summation of the forces in the x direction. They should all be equal to 0. And now we want to simplify everything by dividing by the REV, the represented element volume, which is dx, dy, dz, in each direction. We are going to end up with something like that, which is much cleaner. Right?
Derivative, right?
Yeah, PDE, basically. Yeah, very, very simple equation. And we have it in the y direction too. This is, let me write it down. Sigma fx equal to 0. Oh, sorry. I'm horrible with this.
Okay.
This is sigma summation of forces in the x direction equal to 0. Summation of forces in the y direction equal to 0. And summation of forces in the z direction equal to 0. And then everything can be basically the accumulation term of they cannot be combined together in a matrix form we're gonna see later. The accumulation term can be non-zero. So basically, sorry, not the accumulation. I was wrong when I said the accumulation term is not this. I made a mistake it's the internal acceleration form. Accumulation term is this, okay? It can be non-zero, okay? You may have, it's still a balance, but non-zero on each side, right?
So what's actually the raw AX? It's just to stabilize the forces?
No, it's acceleration term. You're gonna see later, like gravity is an acceleration term. Like it doesn't matter, this thing has a, even if I hold it, I must be balancing the gravity, right? Because if I don't hold it, it's gonna fall. So I'm putting a force on the other direction and sort of indirectly. And this is the summation. Yeah.
Here, but in the still, like in the situation when the forces equal to the same, they are the same. They
It's
have
a
the
steady state, right?
steady state, basically, yeah.
Steady state means
Or iso-
all the derivatives with time go to zero. So you
Yeah.
have accumulation equal to zero. If you say steady state, you come here and you set this equal to zero.
okay.
Doesn't change with time, basically. But it's still summation equal to zero, right?
Yes,
There is still balance of the forces in each
Yeah.
direction.
force balance.
Yeah, regardless, yeah.
Equilibrium.
It's just we want to add a term that may not be zero. And sorry, I made a mistake. I said accumulation before. I saw the A for the acceleration, and I thought about accumulation. The acceleration, this is units of acceleration, by the way. Again, in each direction, you have X, Y, Z. It's how does the speed changes with
Time.
yeah. It's not units of acceleration, it's a little bit more complicated. But the AX, alpha X, alpha Y, alpha Z, they are in units of acceleration.
It's just acceleration multiplied by the density.
Yeah.
The distance by the time square, right?
It's momentum, basically.
Yeah, it's like distance times square.
Acceleration.
Yeah. MS square,
Yeah.
second square. Yeah. Now let's do that, and it's gonna clear things up for the alpha terms. Let's do the application in the vertical stress, in the vertical direction. You will see why I choose the vertical direction, basically Z. I want to show you something where in the vertical direction, alpha X is 0, alpha Y is 0, alpha Z is not 0, it's minus G. That's why I choose the vertical direction. And let me make another, so no accumulation terms. Alpha X, alpha Y equal to 0, alpha Z is given to you. And let's just say no shear stresses. So look at the simplification now. X direction. So this is basically saying delta SXX with delta X is 0, right? Look at the Y. And look at the Z. Okay. I guess the first two are not interesting, but the last one is very important. Look at that now. And then look at what I found. I make a separation of variables. I bring basically I take this, the Z, and then, yeah.
Remove the D with the integral, yeah.
What D? with
Yeah,
D?
that's correct.
Not that D, the D from this side.
Yeah, that's correct, that's correct.
Yeah. And basically I do the integral 0 to Z, and then I get SZZ equal to the integral from 0 to Z rho G dZ. And you have seen this equation before in module 1, which is basically the oververse. Yeah, for SV. That's to clear up the acceleration term.
And the H basically is the DZ.
Yeah, the height of the layer, yeah. So kinematic matters, displacement versus strain. Okay, we talk about stresses. And we said that stresses cause strains, cause displacement or deformation. Deformation, displacement is the same thing. Deformation is a very qualitative term, okay? Displacement, you can measure, so it's more quantitative, but it's not the best in using in mathematics. So we want to come with something better, okay? So think about deformation, very qualitative. You cannot quantify deformation very easily. So you use displacement, but then displacement has units. I prefer something that is unitless so I can play around easier, okay? Stress applications results in solid deformation / displacements and vice versa. However, absolute displacements are not enough to determine stresses. A solid may translate or rotate in space without development of any internal stresses required to equilibrate external actions. Gravity is a form of internal stress. It's applied everywhere, basically. Strains do not quantify the absolute displacement magnitudes, but the displacement variations in space. I know it sounds a little bit too scientific, it will become easier. Relating displacements, we call them, we were gonna use U term for that. To strain, for strain, we're gonna use the Greek letter epsilon. Let's see. Axial strain in the x direction, you have epsilon xx is the change in ux. If something is u, and it becomes bigger u, bigger in the x direction, the change is delta ux. And then I need to divide by the original one, what it was before. Let me make it clearer by showing you this schematic. I was ux in this direction, long. ux feet, let's say, okay? And it became, I apply a certain stress, and it became a ux plus delta ux, right? So now, if I want to quantify this without any units, I will use strain x of a force x in the x direction, delta ux divided by ux. The units for the strain would be no units. Unitless, basically. Same thing with the y, okay? I apply stress, I get a displacement delta uy. The original is uy. Feet by feet or meter by meter, go away. All right. Now for shear, some people use the Greek letter gamma, the small gamma, for shear. So if basically they may say gamma xy. When you have gamma, it basically means that the subscripts are not equal. Just like we have tau for the shear stress. But I use epsilon. Some people do use only epsilon to avoid having too many variables. Just remember when the subscripts are not the same, it's shear. Think of shear. Okay? Now it's a little bit more complicated. Okay? I need to see it a little bit two-dimensional. And I'm gonna have this variation. if I make it. Look at that, I mean X and Y, and then it's shear, so it's a little bit of rotation or like tilting involved. I changing the X and I changing the Y as well.
Have an angle.
Yeah, I have an angle, exactly. Exactly. Look at that. Much more complicated. And yeah, the angle that Malek is talking can be evaluated with this crazy equation. You don't need to know how it is derived. It's a little bit long, but
It's an arctangent, I remember.
yeah, it's an arctangent. When we do about failures in rocks, we are gonna use it.
It's not hard to explain.
Yeah, it's not hard to explain, but it can be derived from this actually. You can draw the line. But yeah, pi is 180 degrees basically, and then you use the arctangents. And we're gonna use it when we see rocks failing, and we're gonna say they fail at an angle so and so from the vertical, like from the horizontal, basically 60 degrees or something. And basically, we're using this equation to come up with that. That's later in module 4. So similar to the stress tensor that we talked about in the first module, we do have a strain tensor. It makes sense that we have a strain tensor because we go from one to another. One is, they are both affecting the other, right? You apply stress, you get strain. You have strain, you get induced stresses, etc., etc. So similarly, we have a strain tensor. Basically, it's an organized way to have the strains that are induced. 6 unknowns, and they are basically very similar to the stresses. You have the normal strains on the diagonal, and then you have the shear strains on the. Let me draw. I think it was blue that I did the stresses, the normal stresses, and then I used orange for the shear stresses. This is shear. This is shear. This is shear. These are shear. These are shear. Now, if you use the gamma instead of epsilon for the shear, this orange is going to be gamma, basically. Just like for stresses, it won't be sigma, it will be tau. Yeah.
Oh, okay.
Did I get it wrong?
So no, so delta UX should be divided by UW, right? So UY. Yeah.
Yeah, it should be the other way.
Yeah.
Yeah. Because it's shear. Yeah, so this is the strain tensor, and it can be related to the stresses. Now we're going to make it volumetric, of course. Volumetric strain is a little bit of a combining many into one, right? How does the volume changes? I'm looking at it as a volume, not in three directions. Now, yes, it's an REV. It has three directions, but I can look at it as a volumetric strain, one value, basically, combining everything into one. The summation of all diagonal terms yields the volumetric strain. In Cartesian coordinates, it's basically the addition of the three. Imagine a cube with initial volume ux, uy, uz, and the final volume is ux plus delta ux, uy plus delta uy, uz plus delta uz. So now I have this, I started from this. I did whatever, applied some sort of stress to it, and I got this. Okay. So how do I quantify? I use these two to quantify my volumetric strain. I final minus initial divided by initial. Final volume, initial volume divided by initial. Exactly how I did with the stresses in each strains in each direction. I did it for the X, I did it for the Y. I showed you in the previous 2 slides ago. It's the same thing I'm doing here for volume. Final volume minus initial volume divided by initial volume. Now, can I mathematically simplify it? The answer is yes. I can multiply all those. I can, let me see, take the first term, multiply by this, take the first parenthesis, multiply by the second parenthesis, multiply by the third, subtract, etc. It's going to be algebraically a nightmare, but I can do that. And let me make my life easier and say, okay, whenever I have 2 deltas multiply with each other, I'm going to set it equal to 0. It's going to be, it's very small, okay? And then also, when I have 3 deltas multiplied with each other, it will also be equal to 0. That's because I assume it's a small deformation. And actually, my whole elasticity theory is for small deformations. So it's valid, it's with that assumption, with that overall assumption. So the volumetric strain simplifies to this. U, Y, UZ delta UX plus UX, UZ delta UY plus UX, UY delta UZ divided by UX, UY, UZ. The denominator stays the same, obviously. But what can I see here? Look at that. I can, this cancels with the, oh, sorry. Yeah, I got the wrong. This, let me get this, cancels with this, and then the middle one is the first and second. Sorry about that. Yeah, okay. So it can simplify mathematically to this. What are those?
Initial.
The stress, the strains in each of the principal. Yeah, exactly.
Basically this.
Yeah.
Basically this. Gonna just be like this for sure.
What do you mean?
The principal stresses gonna translate.
Yeah. We're gonna see how they translate in a vectorial manner, in a matrix manner. Okay. So this is how I get my volumetric strain. And if you took, if you are undergrad, you have already taken solid mechanics, you have gone through this theory of linear elasticity. This is exactly the equations that you did there. No difference here. It's just, in this case, they're applied to rocks. And we haven't even made any deviations from that theory yet for the rocks, which is basically adding pore pressure and then something else that is very similar. Okay. Now, diving a little bit more into linear elasticity, everything that we have seen so far and we will see, it's it's starting from Hooke's law. It's Hooke's law applied in 3 dimensions. Okay, Hooke's law in the X direction, in the Y direction, in the Z direction. You basically assume that the materials that we are interested at, basically rocks, for small deformations, they are good to obey Hooke's law.
Yeah.
Force versus displacement, proportionality. So, you may not know it. If there is an American or an English speaker in the group, may know what term is used to describe qualitatively how does force relates to the displacement. How much force do I need to make this much displacement, let's say, unit of displacement. What sort of quality, like what feature, what characteristic do we say? Oh, this, I apply this much stress and this only moves this. But then I have a material that is,
Strong?
no, we are close though. Stiffness,
Stiffness.
yeah. Stiffer material, I need a lot of force to cause this displacement, right? Versus a softer material, I need to less.
Toughness or stiffness?
No, stiffness, yeah, stiffness. So this is what interrelates the two, force and displacement, okay? We have a force in the z direction applied on a cross-sectional area A. So if I make the force divided by A, I get stress. And then on the other side, I have displacement delta z, which I haven't shown. Look, I think it's a, if I do it, it's gonna come in slowly. There you go. Look at that.
Ooh.
You apply Fz and you get a displacement delta z. So you make the height taller by delta z. So I cause this displacement delta z from my original height. So what is on this side, on the left side of the, let me draw on the thing because they might not see me. On the left side of the equation is a stress. On the right side of the equation, this one is basically strain, exactly. I'm relating stress to strain, and I have a constant of proportionality, E. What does this E tell me? No, I mean, before the name, but like qualitatively.
The amount of the stiffness.
Yeah, the stiffness, yeah, exactly. The stiffness, okay. So if this E is big, I need a lot of stress to cause a small displacement.
Yeah, displacement.
If it's small, I go like this. So what do you expect to have a bigger E? Wood or steel?
Steel. Steel is metal, right?
Yeah, I think, yeah, steel is metal. Like,
Steel.
I don't know the top of my head the wood, but I think it's smaller.
Yeah.
But I know steel is like 30 times 10 to the 6 psi.
Like pure steel.
Yeah. Reinforced or whatever. Like something like very, very stiff.
Yeah. Carbonates and shape, for example.
Yeah, those are. We haven't gone into rocks yet because then we have to do the pore pressure and stuff. Then Young modulus represents stiffness of the material. We said that, and basically sigma on the left, E epsilon on the other side. In fact, if you see it correctly, this side is basically sigma zz. This side is epsilon zz because in the z direction, right? And we measure that E in the lab using what we call the UCS test, unconfined compressive stress test. It's actually strength, not stress. Yeah.
It's a destructive test.
Yeah. You break the samples. It's a destructive test. As Malek said, it's like you put something that you don't want to use anymore inside that. In that case, yeah, and we're going to talk about it later on in this class, but really we're going to talk about this kind of test in the next class as well. Okay, so we know E now, Young's modulus. We know what is used to interrelate axial strain in one direction to stress into one direction, right? Remember, I wrote sigma zz and epsilon zz. I didn't write sigma xx epsilon zz. I didn't write sigma xy epsilon yx or something, right? It's important that it was the same, okay? So that's why here I have E refers to the stress and displacement along the same direction. So Look at that, sigma y, II, epsilon II.
Same direction.
Same direction, exactly. In the rock, sometimes we use axial, but then we don't have cylindrical coordinates. So axial is always in one direction option, right? Z.
If we take 3 courses.
Yeah, you can do,
Back.
but then this is X, Y, Z as in Cartesian.
Yeah.
Yeah, you can do it for X as well. You can do it for Y as well in Cartesian. The solid will most likely shrink in the direction perpendicular to the applied stress. Okay, so I have this material. I apply the same stress I applied earlier. I make it longer.
Yeah.
What's going to happen to the width? It's going to get narrower. What about if I push it and make it shorter? It's going to become fatter. Yeah. So I have a reaction on the perpendicular direction, orthogonally. So I need to have another material. So basically I have the old one. It was like something like H. I applied stress FZ, cross-sectional area A. And I achieved elongation, was it delta Z, something like that. Okay, by the stress FZ. But also, I have a reaction in the opposite direction, which is, okay, it became longer, but it became slimmer as well. So my delta Y, there is a delta Y induced, or a delta X, right? Okay. How do I quantify that? So we have the Poisson's ratio, which you also learn in solid mechanics, is defined as -1 times the ratio between the strain perpendicular to the applied stresses. So this is the equation. I have a strain in the J direction that is induced by what is causing the strain in the I direction. And also bear in mind that you may have, here the only rule is that J is not the same as I, okay? So if the I is X, J can be Y or X or Z, as long as it's epsilon YY or epsilon ZZ, right? So you can have 2 options here in a 3-dimensional space. Now, typical for rocks, values range from 0.1 of Poisson ratio to 0.4. By the way, from the equation that I showed earlier, what are the units of strain?
The distances.
Yeah, but what?
Unitless.
Unitless.
Yeah.
What is the unit of Poisson ratio?
Unitless.
Unitless.
Yeah.
Right? What is the unit of Young's modulus?
It's stress unit.
No. Yes,
It's unit of stress.
Dimensions of pressure? Yeah.
Yeah.
Dimensions of stress? Yeah. So for rocks, let's just say 0.1 to 0.4 is the average. It's possible to have a material that has a negative Poisson ratio. A foam has negative Poisson ratio, something that expands in all directions. Cork of a wine bottle has a negative Poisson ratio.
Cork, you need a.
Yeah. Cork. Yeah. We call short people in Greek, we call them cork. But it's impossible to have a Poisson's ratio above a 0.5. Okay? Above a 0.5, you violate the laws of thermodynamics, the laws of physics. You are basically telling me that you can put more energy, you can get more energy out than what you can put in. And in fact, you need to know this because there was a student this year in Arma, he had a poster where he said that I ran some tests and I got Poisson ratio of 0.7. I mean, you can perhaps get a reading that is 0.7, but you need to know like how it works. Like it's an apparent value. It means that something is going on. Something is applying external force, applying energy inside it. So I would say if you see a rock that has less than 0.1 and bigger than 0.4, pinch yourself. It might be in the wrong side, especially if it's over 0.5. Now, your TA works with gelatin, does experiments on gelatin. This one has, you can assume that has under the right conditions, has a Poisson ratio of 0.5. Maybe if you use 0.5 exactly, you get some mathematical, no, is you use 49, 48, yeah. It's a little bit of an asymptote. You can get close to it, but not exactly there. If you have a 0.5, it means that you have no energy losses anywhere. Like you have no friction between the surfaces. Like if you apply the stress in one direction, getting the displacement in the other direction, etc., etc. But yeah, 0.5, don't even think about it. Okay, it's impossible. The real behavior of rocks differs from linear elasticity assumptions. You have some things in the rocks like anisotropy, heterogeneity. In addition, you have pore pressure that we learned in the first module. So there are some deviations that we need to put in our theory to make it applicable to rocks. And we are going to see that later on in this week. Yeah, often rocks are not perfectly parallel or contain micro cracks. Both features make the initial stress-strain behavior appear less stiff than the actual stiffness. So we are reading we are reading in the lab a higher stiffness than what the rock is behaving as. After this, the rock may display linear response, good correlation for calculating E, followed by softening while approaching its peak stress. So what I'm saying here is I have a code and I'm testing it in the lab. I'm putting it in the lab and I'm going to apply stress on top of it. It has micro cracks in it and empty spaces. Once I apply stress, the first thing that we'll do is that the micro cracks are going to close. So you're going to get a lot of displacement for that stress that you are applying, because you have displacement from cracks closing, but this is not the rock like becoming shorter. Really, it's the empty spaces you are getting rid of empty spaces.
Or the pore is gonna shrink.
Yeah, that's why you are appearing that it's less stiff than what it really is. You are measuring a smaller value. And then you keep applying stress until you get it to crack. And from the stress that you need when it cracks, you get the idea of the basically the Young's modulus, etc., etc. And in the next class, we are going to try to simplify that with a different notation, a notation put together by a musician called Voigt. We're going to talk about him next class. And his work is what made it easier to show things symbolically using matrices. And if you are using MATLAB, or you are definitely using Voigt's notation for stress and strain problems, MATLAB is actually matrix laboratory, and they all use the Voigt's notation. He arranged them in the matrix a certain way that makes it easy to model continuous mechanics, a continuum, stress and strains on a continuum material. And we're going to talk about it in the next lecture. Meanwhile, take a look at the homework. I think you can start it by now. The homework too, I mean. homework one is due tonight. I'm gonna talk about it, I'm gonna overview it probably next lecture. And I have office hours tomorrow if you have any questions, 1 to 4. And I'm also available by email and the TA, same thing as the TA. Thank you very much. Have a nice rest of your day. Have a good evening.